Hey guys, I thought I'd do a quick screencast to review some related rates and some optimization. I realized the picture didn't come through for number 2, but we can work our way through it anyway. All right, so here are two A/B style multiple choice that have to do with optimization, just to sort of think about what it is that we were doing there. I encourage you, if you're looking for more, to look back at that section in the book. And I'm happy to look over some work today if you'd like. Consider all right circular cylinders for which the sum of the height and the circumference is 30 centimeters. What is the radius of the one with maximum volume? Okay, so this is one of those classic problems where we're given some sort of constraint and we're gonna have to plug that in to find our maximum. Okay, so again, with all of these things, I encourage you to try them before you watch. So let's think about this. We're trying to maximize. Remember, we always say trying to max volume, and the volume of that right circular cylinder, of course, is just pi r squared h. Okay, and this has two variables. So if we were to take a derivative right now, we would get into all kinds of trouble, right? The product rule, and it would be gross. So we want to eliminate a variable by looking at this constraint here, which is that the sum of the height and the circumference is 30 centimeters. So I think that means that 30 is the sum of the height and the circumference, which is diameter times pi, or 2r pi. Okay, so I'm just going to quickly say h, that means it's 30 minus 2r pi. And then I can plug this in for this h up here. So we'll get v equals pi r squared, and then times this h, times this h. Now I have an equation with one variable. And remember, we're trying to max this thing, so we're going to have to take a derivative. So I'm going to simplify this a little bit. Ooh, pi squared, that's kind of exciting. And we want to find some critical points. So we have to think about what v prime is, right? And v prime, of course, is just 60 pi r. And then this thing, which is 6 pi squared r squared. Okay, and we're going to have a critical point where this thing is 0. And when thinking about these problems, right, this is always going to be a max. And you can do a first derivative test and look at the sign of v prime to around the critical point to verify that for yourself. Or you can think, hey, the boundaries where the height is 0 isn't going to yield maximum volume because the radius won't be, massive. And same where the radius is 0, the height can only be 30, right? So there's no like 0 times infinity here. It'd be 0 times a finite number, so that's going to just be 0. So anyway, what we're going to find is going to be a max. So we're going to find this critical point here. And again, we know it's going to be a max. I'm happy to talk to you about that if that was unclear, right? But again, you can look at the sign chart and sort of say it's a max. So we're going to divide by 6 pi r, right? 6 pi r and be left with pi r equals 10, or r equals 10 over pi. So I think it's this guy down here. Okay? Again, that's the r that gives that has a critical point for v, right? So this one, my picture didn't come through, which is kind of sad. But if you can envision the curve here, and then you can try me. You can envision the curve here. This guy here is this curve is y equals 1 over x squared. 1 over x squared, okay? And then we can build this little triangle, or this little rectangle somewhere here with proportions will be all off. But we'll say this is 3 comma 0, and over here we have x comma 0. And this can sort of go up to the curve over here and down. So this point would be x comma 1 over x squared because it's on the curve. And this point here would be 3 comma 1 over x squared. Okay, we're trying to maximize the volume or the area of this rectangle, right? And so if we think about the area is just going to be base, which is x minus 3, times the height, which is 1 over x squared. And we're trying to maximize that, trying to maximize this. Okay, and this is one where you might say, oh, well, maybe it's infinite. I don't know. Again, you should look at your sign chart and verify that it's not. So we're going to be left with what? What is this? X to the negative 1 minus 3x to the negative 2. And and therefore the derivative is negative x to the negative 2 plus 6x to the negative 3. And we're trying to find a critical point, which is where this is true. And that's going to be true where 6 over x cubed equals 1 over x squared. All right, x clearly can't be 0. We can multiply by it. I guess in this case we're dividing by it. But when I multiply by it, I'm going to get x equals 6. X equals 6. And again, if you thought about the sign of this thing, SIGN of this thing, around 6, you could see, maybe that things are going from positive to negative in A prime. Which again is an exercise I encourage you to do for these multiple choice questions on the AP, right? We can sort of, we sort of just know that it's going to be a max. Okay, so on to related rates. A spherical snowball is melting in such a way that it maintains its shape. The volume of the snowball is decreasing at a constant rate of 5 cubic inches per minute. The instant when the radius of the snowball is decreasing at 3/5 inches per minute. What is the radius of the snowball in inches? Okay, and they give us this formula. So this one is sort of a vanilla related rates question, right? Because I could just go straight to taking derivatives with respect to time. So dv dt equals 4 pi r squared dr dt. Okay, remember when we take the derivative of r, it's a function of time, right? So we have to say r squared dr dt, and the 3 came out and canceled with that 4/3 at the beginning. So what do we know here? What can we plug in? Well, the volume of the snowball is decreasing at 5, so it's negative 5 over here. And the radius is decreasing at a rate of negative 3/5. Okay, cool. Only got one variable to solve for, so let's try to do it. So I'm going to say this is what, well, the negatives cancel, so we have 25 over here over 12 equals pi r squared. So r equals root 25 over 12 pi. Oh, this one, right? Sorry, because they simplified the top. Okay, good. So again, this is another instance, right? You get some answer, and then you might not be sure that the AP got it, but there it is. Okay, and then lastly. Well, I guess lastly for my multiple choice. Functions w, x, and y are differentiable with respect to time and are related by the equation w equals x squared y. If x is decreasing at a constant rate of 1 unit per minute and y is increasing at a constant rate of 4 units per minute, what rate is w changing with respect to time when x is 6 and y is 20? Okay, so this one we're going to be forced to do the product rule, it looks like. So when I take my derivative of this thing with respect to time, the left side is easy. The right side's tricky, right? Because I have two functions, this red one and this green one, that change with respect to time, right? So we have to do the product rule. So if I take the first times the derivative of the second, that's just dy dt, plus the second times the derivative of the first. And the derivative of x squared is 2x dx dt. Again, we have to chain rule it. Okay? And then we're just plugging a whole lot of stuff in. So we're solving for dw dt. Oh boy. X is 6. And dy dt is 4. That's a big number. And y is 20. And x is -1. Okay. And dx dt is... Sorry. That's dx dt. X is 6. Dx dt is -1. And I suppose I would have gotten the, same thing if I'd reversed those, but that's a different story. So 36 times 4, that's 144. And this thing here is 240. Ugh. -96 units per minute. Good. Sorry, didn't see the negative sign there. Yeah, bad on the, maybe they should have units there on their answers, but that's okay. All right, so let's think about this free response question. And I didn't give myself very much room. So oil is leaking from a pipeline. This sort of requires related rates and a little optimization, maybe at least to think about. Oil is leaking from a pipeline, blah, 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 blah. The oil slick takes the form of a right circular cylinder with both its radius and height changing with time. It's kind of exciting. At the instant when the radius of the oil slick is 100 centimeters and the height is 0.5 centimeter, shouldn't that be centimeters? The radius is increasing at the rate of 2.5 centimeters per minute. At this instant, what is the rate of change of the height of the oil slick with respect to time in centimeters per minute? Okay, so let's think about this volume formula. Pi r squared h, as they're saying. And since we're given everything and we're not really given a constraint sort of equation, we need to just plug stuff in, right? So if I take my derivative here, very similar to our last exercise, right? I'm going to have this pi r squared dh dt. And then I'm going to have pi times h times 2r dr dt, right? Because again, we have to take that derivative. And let's just shove everything we can into here. So what do I know? I know dv dt is 2,000. I don't even know what I'm solving for. The rate of the dh dt. Okay. Equals pi and then r squared. R is 100 right here, it looks like. dh dt. And then the height is... How do I know the height? Oh, 0.5. 1/2 times 200 dr dt. 2.5. So, we gotta solve for this thing. That's massively unpleasant to do. Yikes. So this is going to be a decimal. I'm guessing this was a calculator active problem. Or maybe they were just happy with you doing this without that. But it's going to be, anyway, it's going to be 2,000 minus, what is that? 250 pi. This thing's 250 pi, I think. Right? 100, yeah, 250 pi, okay. Divided by 10,000 pi equals dh dt. I skipped some steps there, but you guys could probably do it. I'm going to punch that into Google really fast, just in case we want a number. Okay, and I got 0.03. We always use 3 decimals on the AP, by the way. I got 0.03866. Right, you can keep going as many decimals as your calculator wants. Here's an instance the AP would probably be okay with 0.038 or 0.039, but we don't, just give them more than they need. Okay, and that is centimeters per minute. Centimeters per minute. Okay. A recovery device arrives on the scene and begins removing oil. The rate at which oil is removed is 400 root T, cubic centimeters per minute, where T is the time in minutes since the device began working. Oil continues to leak at the rate of 2,000 cubic centimeters per minute. Find the time T when the oil slick reaches its maximum volume. Okay. I don't think this one's so bad. So, this thing, right? This thing is going to catch up and eventually be going at the same rate that oil is leaking in, right? Where at the start it's going at 0 cubic centimeters per minute, but then eventually it'll get up to 2,000. So I think we just need to find that point. So, a recovery device. So let's think about a new expression for the volume of my oil slick. Right, the volume of the oil slick is really like 2,000 T, because that's how much it increases by, right? It increases at 2,000 T per minute, minus 400, well, I guess it's the rate. We don't even want to think about it like this. We would just want to go straight to dv dt. we know dv dt is going to be 2000 minus this r of t, minus 400 root t. We don't want to integrate that if we don't have to, right? So why even bother with the volume, the actual volume? We don't need to worry about that. It's bad. Okay? So, and we want to know when this thing reaches a maximum. And so max will be attained when dv dt equals 0. So we're saying, when is this true? Well, that's true. Sorry, my little one is here. That's true here when root t equals 5, right? When root t equals 5. So of course t is just 25, right? Just 25. And let's see if that makes sense. At t equals 25, r would certainly be 2000. Our r of t would be 2000. So 25 minutes in 25 minutes is when this thing would reach its maximum volume. And again, that's because if you think about r of t starts at 0 and it's going to go up infinitely, right? 400 root t it's not ever bounded above, right? So at some point it's got to be 2000, little intermediate value theorem there. So you know it has to be 2000 at some point, and that occurs at 25 minutes. Okay, so by the time the recovery device began removing oil, 60,000 cubic centimeters of oil had already leaked. Write, but do not evaluate an integral expression that gives the volume of the oil. So this is kind of what I was getting into in the last one, right? I was getting ahead of myself. So the volume at 25. So let's think about that. At the volume at 25, V of 25 has got to be this 60,000. That's sort of what was in there, right? Plus 2,000 times. Well, I guess we could just give two expressions. Okay, so we could either just integrate this thing down here and say, oh look, I know this is going to be the integral from t equals 0 to 25 of the rate, right? Of the rate. And that's certainly fine. Or we could pull that 2,000 out, right? We could have said, okay, I know that 60,000 was in there at the beginning, and then we've been sort of going at this other rate, right, where I have 2,000 per minute, right? So that's another 50,000 that have flowed in. And then I'd have my, how much did we remove? Either one would be fine. Okay? Just sort of depends on how you think about it. They'd both be good. So yeah, again, if you have questions, please reach out. I should have some good time to respond today. But enjoy preparing for our little quiz.